All right, now I'm going to start talking about lecture 3, part 2. Again, it's going to be focused on predicates and implications, and we're going to solve a bunch of problems together. Again, the best way to do this is to pause while I start a problem and try to solve it on your own, and resume the video to see, if your solution matches the solution provided. Okay, let's get to it. So the first part, actually, I'm going to go over a leftover question from lecture 2, where I feel like I did not give enough time to go over this carefully, especially for part B. So let's do it together one more time for this number sequence question. Okay. Of course, if you already understood this, you can feel free to fast forward. So the question is, if I giving you a closed formula as it's written here, how do I get a recursive formula? Okay. So the interesting part of this is that if you give me a closed formula for an, the first step I want to understand is what is a closed formula for an minus 1. So the way I would do it is substitute n minus 1 into this formula. So what's already given to me is an is equal to 2 to the power of 2n minus 1 minus 1. Okay. And now, if I substitute n minus 1 in there, I have an minus 1 is equal to 2 to the 2 times n minus 1 minus 1 minus 1. Okay. So the way I substitute is I know n is actually a variable, and I'm going to replace n by n minus 1 in the formula. That's what I do. Okay. So now, what is the next step? And there is actually a simplified version than the first version I gave, which is a little bit confusing. So now I'm going to do a slightly more simplified version of the solution. Okay. So what I'm going to focus on is, if I look at an, the formula for an, it has a term that says 2 to the power of 2n minus 1. So somehow I would like to be able to express this term using an minus 1. Okay, so how do I do that? One of the rule, one of the algebra rule you need to be familiar with is am minus n is equal to am divided by an. Okay, so this is a rule we're going to use for this. Again, if your sort of background over algebra is a little bit rusty, I would suggest spending some time review some of the basic algebra concepts. Okay, so now let's get back to an minus 1. So what I will do is I will expand the power to be 2n minus 2 minus 1. Okay, nothing special here. And then further, I'm going to switch the order a little bit. So instead of 2n minus 2 minus 1, I'm going to do 2n minus 1 minus 2. Okay, so now I'm going to apply the rule I wrote involving a to the power of m minus n, where my m is this piece here, and my n is this piece here. Okay, so if I do this, this is equal to 2 to the power of 2n minus 1 divided by 2 to the power of 2 minus 1, which is equal to 2 to the power of 2n minus 1 divided by 4 minus 1. So what I just got is that I now have expressed an minus 1 in terms of a formula that involving the same term, 2 to the power of 2n minus 1, that shows up in an. So what can we do? Now we solve for this variable, treating this as a unit inside the equation 2. So what do I have? I have an minus 1 equal to 2 to the power of 2n minus 1 over 4 minus 1. The first step I do, I add plus 1 on both sides. So again, this is algebra. And now I multiply 4 on both sides. So now I'm good. Now in this equation, I solve it for this yellow term in the form of 4 times an minus 1 plus 1. So I can substitute this term into an. So now going back to equation 1, I have an equal to 2 to the power of 2n minus 1, but we just found out this equation 3 is that 2 to the power of 2n minus 1 is equal to 4 times an plus minus 1 plus 1 and minus 1. This is equal to 4 times an minus 1 plus 4 minus 1, which is 4 times an minus 1 plus 3. That's it. My final solution is an equal to 4 times an minus 1 plus 3. Okay? All right. So now let's move on to the next question, which again, I want to revisit this again at the end of lecture 2, is how do I use a truth table to derive sort of the solution for this problem, okay? And the key of it is actually the idea, well, I'm going to use green, the idea is that you want the input somehow have to match the output. Okay, this might sound confusing right now, but let's make it more clear. What do I mean by input? So remember, A made a statement, B made a statement. And in the previous version of this question, we say, I'm going to use two variables, P and Q. P represent A is truthful. Q represent B is truthful. So this is what I call input. The truth value with respect to P and Q is my input. Again, in my truth table, the first column is basically asking, is A truthful? Which is basically the possible value for variable P. The second column is going to ask, is B truthful? And it's going to correspond to the variable Q. The fourth column is now A statement. So A says, both of us, A and B, are telling the truth, which is a statement P and Q. And then the last one is B made the statement that A is lying, which then we translate to not P. Okay? So now the first thing we do is to derive the truth table. Okay? So if P is true, Q is true, true, false, false, true, false, false. Those are all possible combinations of variable P and Q. And then I'm going to correspondingly fill the rest of the truth table. So this is true, false, false, false. And then this is false, false, true, true. So nothing surprising. I'm just filling the truth table. But what's really interesting is how do I derive the final conclusion, who is lying and who is not, based on this truth table. And this is going back to my statement, input have to match the output. So what is input? The first two columns are considered the input because it's a variable P, variable Q. The third and the fourth column are going to be my output, okay? So again, let's make it more clear. What do I mean input have to match the output? Think about the following statement. If A is not truthful, which also means if A is lying, then what A says is false, right? So if A is lying, then what A says has to be false. On the other hand, if A is truthful, then what A says is true, right? So if A is always telling the truth, then what she said has to be true, right? So if A is truthful, what she said has to be true. So now this is where the interesting thing happened when I say input have to match the output. So let's start from the third row, okay? I start from left to right. If A is not truthful, which corresponding to P to be false, if A is not truthful, then based on the logic I just wrote down, if A is not truthful, meaning that if A is lying, then what A says has to be false. So, if the first, on the third row, if the first column is false, then the third column has to be false, right? So again, this is based on the things that if A is lying, then whatever A says has to be false. So they match with each other. Great. Now let's look at B. B is saying it has a value, the Q has a value, the second column has a value of true. What does that mean? That means B is truthful. Again, if B is truthful, then whatever B says has to be true. That is indeed the case if you look at the fourth column, because that is what he says. So, false of the first column match to the false of the third column, true of the second column match to the true of second column. So this is great. This leads to the conclusion that A is not truthful, meaning that A is lying, and B is truthful. That is a conclusion, right? So if I answer this question, that is A is lying and B is truthful. Now you might ask me the question, okay, so what happened to the first row, second row, and the fourth row of this? So let's do it again. Okay, so look at the first row. When A is truthful, meaning that this column is true, then what she says has to be true. Great, they match with one another. Input match output. However, if I look at the second one, when B is truthful, that means whatever B says has to be true. However, there's a mismatch. In this case, I'm using dotted line, means mismatch. When B is truthful, but what B says is false, so that is a contradiction, or that's a mismatch. So I can't draw conclusion from the first row. Again, focus on second row. When A is truthful, okay, then whatever A says has to be true. However, there's a mismatch because whatever A says is actually false in this case. So there's a mismatch, meaning that there's a contradiction. Similarly, with the last row, when A is lying, then, whatever A says has to be false. So this is great. They match with one another. Now, if we look at B, when B is lying, right? So Q is false, B is lying, then whatever B says has to be false. However, there's a mismatch because according to this truth table, whatever B says is true. So there's a mismatch. Again, that's leads to a contradiction. So the only time where input matches the output is the third row. That leads to our conclusion that A is lying and B is truthful. Okay? All right, so now let's move on to more logic problems or Boolean algebra. So you might have seen this for lecture 2, and now we're going to do it in terms of using propositions. So my first one is, well, X and Y are real numbers, so I'm going to define P to be the statement X is positive, and Q to be the statement Y is positive. Okay? So now for the first one, both X and Y are positive. Okay, this is where you want to pause it and try to solve it on your own to see if you get the same solution as I do. Okay, so both X and Y are positive. That means both P and Q is true. So I have P and Q. Second one, at least one of them is positive. Then it means the first one is positive or the second one is positive. So at least one of them. They can be both positive, but at least one of them has to be positive. Again, this corresponding to the OR operation. Okay. Now the next one is exactly one of them is positive. That means they cannot be both positive. Then we have to pay, be a little bit careful here. What you get here is if P is positive, then Q cannot be positive. So if P is positive, then I have an AND condition that Q is not positive. And if P is not positive, then Q has to be positive. That's the second one. And then there is R or condition between them, right? So what does this or condition mean? It means either P is positive or Q is positive, but not both. The next one is neither of them is positive. So what is not positive mean? That means not P, means P is not positive, X is not positive, not Q means Y is not positive. So this is going to be an and condition between these two, okay? All right. Okay, I'm just giving more space if you want to solve it on your own. Now the next practice problem we want to do is prove logical equivalences using theorem 2. So this following table is again theorem 2 from the textbook, okay? So I have a new slide to give you a little bit more space. Okay, again, this is place where you want to pause it and try to solve it on your own and then match your solution with mine. Okay. So how do we want to do this? We do it from left to right. Again, I'm going to copy the statement on the left. The first thing you might want to do is when you observe this proposition is that you notice there is a negation operation outside the parentheses. So the first thing is to say, well, maybe I want to bring it in, okay? So I want to bring it in onto the first term. So when I bring it in, I get negation of P and negation of Q. What is this rule? This is De Morgan, right? De Morgan is when you have a negation on the outside, you bring it in and then you flip the direction of the arrow. Okay. So that's what you get. And now I just copy the rest of it. So this is using De Morgan. Now let's do the next thing. Now if I see the term on the right-hand side, I'm going to see a little bit pattern. There is a shared term, negation of P, and then there is, negation of Q and Q. So this might remind you of distributive rule, okay? So I'm going to apply distributive rule here. I'm just using a shorthand of a distributive here. Distributive rule, you're actually applying from right-hand side back to the left-hand side because you have already distributed the terms, you bring it back, and in this case, the shared term is the negation term. Okay, so we bring the negation outside, and then the rest of it inside. This is a distributive rule. And now what's interesting you can notice is I have this term, which is not Q or Q. This looks familiar in terms of, it looks like it's, it has particular sort of a negation flavor, but let's be a little bit more careful. I can add an extra layer of this. Let me just switch it a little bit, like switch the location between these two. This is just applying commutative rule. Just look a little bit more familiar to you even. And the next thing you want to do is this is now I can apply negation rule. Why? Because negation rule is basically if I have a variable P and its negation, it's always true. So that is applying negation rule. And finally, you have a variable and a tautology, and that is identity. Okay, again, this is identity rule. So in some sense, when you have a variable and a tautology, the truth value is always dependent on the variable itself. Okay, all right. Okay, this is just a better written form. Let's move on to the next one. Okay, let's see, are they the same? Oh no, actually those two are the same. I just wrote one more copy so that you can try to do it one more time on your own. I'm going to put this question here because I want you to try it one more time. I have already gone through this in lecture 2. So if you don't know how to solve this one or you're not sure, I would encourage you to watch lecture 2. Okay. I think it's lecture 2, part 2. Okay, let me give one more example of proving logical equivalence. Again, this is a common problem that is going to arise in quizzes and homeworks. So again, I want to prove logical equivalences. I'm going to move from left to right. This is a time where you can pause the video and try to solve it on your own. Okay, and I'm going to do it from left to right. The first thing I'm going to do is to make it look slightly better. I'm going to switch the order, just commutative rule. Okay, and now I have this form. It looks like I can actually apply distributive rule, right? Because distributive rule is when you have, you know, or operation on the outside of parentheses and you kind of distribute the forms. So in this case, I'm treating negation of P to distribute as you apply distributive rule. And once you have distributive rule, the next thing you do is to look at the first term. The first term is negation of P or P. Again, this looks familiar because it's exactly the negation rule, meaning that it's always true. Okay, this is Q. Okay. Okay, so now you have a variable and a tautology, okay? So what does that mean? That means, well, you know, if I wanted to be a little bit careful, I can also, again, apply commutative rule. Again, just switch the order. Commutative. And it's a variable and a tautology. So that is always equal to the variable itself. And this is using identity. Okay. All right. So there's a few tricky part of this question. The most tricky part I would consider for this question is this particular part, is applying the distributive rule. The moment you have applied that rule, you start simplifying things further. Okay, so this is probably the most tricky part of this question. Similarly with this question, I would say the most difficult part is the De Morgan's part, and again, distributive part. And everything else should be followed relatively easily. Okay. All right. So now, as for part 1, we talk about negation of predicates or quantified predicate. So again, this is what I'm going to do. You have 4 minutes. This is time you can pause and try to solve it on your own. And in the next page, I'm going to solve it on my side, and you should match your solution to mine. Okay. So what do I have? Remember, there is, let me just use this space right here to give you an overall view. If I have a negation of some for or, you know that I'm going to get something like this. Of course, I'm simplifying this a little bit. I'm not repeating the rest of the predicate, but typically when you bring the negation inside for all, you get existence. If you bring negation inside existence, you get for all. Okay. And then if you have equality, if you negate it, it became inequality. If you have inequality negated, you get equality. Okay. And what's more, if I have inequality, if say, you know, negation of x bigger than 0, then you get something like x smaller or equal to 0. And finally, there's a negation you might see is if I have negation of A or B, you're going to flip the direction of the arrow to be not A and not B. Okay, so this is just a quick overview of what might happen when you bring the negation inside. So let's do it one by one. So in this case, when I bring the negation on the first term, I have for all symbol, so I know I'm going to flip it. So this became exist symbol. And when I bring the negation to the second term, right? So it's negation of x squared bigger or equal to 0. I put negation on the outside. This now equal to x squared smaller than 0. Okay, that's it. Right, negation of bigger or equal to 0 is less than 0. Next one, oh, to be fair, this should take you maybe 1 minute. Next one, I'm going to, again, going from left to right, but I'm going to do it one by one again. I see the first symbol is existence. When negation, it became for all. The second symbol is for all, it will become existence. And next one is equal. If I take negation, it's now not equal. So that's it for this one. For the next one, I have for all, then became existence. Another for all became existence. Existing become for all. Equality become inequality. So this is, again, existence, oh sorry, for all become existence. For all become existence. Existence became for all. Equality become inequality. Oh, no. Variable z. All right. Okay. Again, this is a solution. Now, this problem became slightly complicated that if I want to negate an English statement, I have to go through a few abstract thinking. The first thing is to translate the English statement to be a sort of proposition statement involving some variables. And then you negate that proposition, and then you translate it back to English, okay? So the first statement is, or you have used, so again, this is a time where you can pause it and try to solve it on your own. And I'm going to solve it in the next page, okay? So now in order to negate the following statement, the first thing I'm going to do is going to translate it into a proposition involving variables, okay? So to do that, I first have to define some variables. I'm going to use U to be the set of University of Utah students, okay? And S, lowercase s, to represent a student. The statement to say, or you of you students live in dormitory, if I translate into quantified predicate, is going to be for all student, that is a university student, University of Utah student, okay? The student lives in a dorm, okay? So for all student, that's University of Utah student. So if all student is in the set of University of Utah student, the student lives in a dorm. That is the original statement. Now I want to take a negation of this statement, right? Again, I have for all symbol, it became existence symbol. And S lives in a dorm become S does not live in a dorm. Now I have to translate this proposition back to English. What does it mean? It means there exists a student who is a U of U student who does not live in a dorm. Okay? Now let's get to the next one. All CS major have red hair or are over 5 feet tall. Okay. So again, I'm going to use capital C to be the set of CS majors. Again, S is a student. Okay. When you say for all majors, they have red hair or are over 5 feet tall, that means for all student, that is a CS major, its hair, S hair, is equal to red, or, okay, so or, I'm going to use this symbol. The statement that S, the height of S, is bigger than 5 feet. Okay, so now I need to negate this statement. Just copy the statement over, but I put a negation in front of it. So the statement has for all, so it became existence. And now this is the thing where I put a negation of A or B. This is logically equivalent to say not A and not B. So what is not A? Not A is S hair, not red. So the student does not have red hair. And S height is smaller or equal to 5 inch. So if I translate back to English, is to say there exists a student who is a CS major, whose hair is not red, and whose height is no more than 5 feet tall. That's an English statement. Now let's go to the next one, okay? Some CS students are over 25 years old. So it means some, it translates to there exist, okay? So it says, let's say the T corresponding to all CS 2100 students. When I say some student have a certain condition, so I will say exist a student that is a 2100 student such that its age is bigger than 25. Now I'm going to put a negation in front of it because I'm negation existence. This is logically equivalent to for all, right? So for all student who's 2100 student, their age, because it's negation, so I'm going to change the direction of the inequality. The age is smaller than 25. So what is the English translation? For all student who is a 2100 student, his or her age is less or equal to 25. Last one. For every integer, there exists an integer y that is bigger than x. This is actually quite easy to do. For every integer, so that is for all integer, z means integer, there exists an integer such that it's bigger than x. So this is a very direct translation from the English. Now I have put a negation in front of the statement. I just copy over the statement. Existent for all translate to existence. Existence translate to for all. And inequality flip the direction. So y bigger than x, y smaller or equal to x. That's it. Okay. So now this is just a typed in version of my solution, and you can kind of match the English statement. For example, the last one, the English statement is there exists an integer that is at least as big as every other integer. Okay. Now we have another statement, practice problem, 2 minutes. In order to do that, you first have to translate the sentence into a logic expression, and then you can take the negation of it, okay? So let's say, what is this? For every 2 real number, x and y, there is an integer that is nested between them, okay? So the way I can write it is to say for every, that means for all x, that is a real number, for all y, that is a real number, there exists an integer n, which is a set of integers, such that n is nested between those two. That is a statement. And now if I take the negation of this, just copy it over. For all become exist. And exist became for all. And now the last bit is interesting. What is the negation of this thing? This thing can be translated to two conditions. X smaller than n, and n is smaller than y. Okay? So now I'm going to take the negation of it. Remember, negation of A and B is negation of A or negation of B. So that's what you get. So in this case, it's x bigger or equal to n, or you can use the symbol, not the symbol or symbol, n is bigger or equal to y. Okay. So how does this translate to English, right? I mean, of course, the question is which statement is true. The first statement is to say, for every pairs of real numbers, there exists an integer that is nested between them. The second one is to say, for there exists a real number x and a real number y, that for all integers, that either x is bigger than the integer or y is smaller than the integer. It turns out that the second statement, which is a negation, is true, but the original statement is not true. Why the case? When you want to prove something that is not true, one way to do this is to find a counterexample. And you are going to see this a lot for when we start studying proofs, which is chapter 2. Counterexample for the original statement, okay? Original statement is to say for any or every two real number, there's an integer between them. But what if my number x is equal to 1.1 and my y is 1.2? There's no integer between 1.1 and 1.2. That is a contradiction. So there does not exist n that is an integer such that n is bigger than 1.1 and smaller than 1.2. Okay? All right. So now let's look at problems surrounding implications. Well, there's always this joke, so-and-so walk into a bar. So let's look at one example here. A police walked into a bar, and then the police collected the following information. The law says if someone is drinking alcohol, then that person is at least 21 years old. What the police has observed is Al is 19 years old, Betty is drinking cola, Cindy is drinking beer, and Dan is 25 years old. What the type of conclusion can the police, imply? So this is what the hypothesis is. P is someone is drinking alcohol, and sort of a conclusion is that person is at least 21 years old. So P implies Q, meaning that if someone is drinking alcohol, then that person is at least 21 years old. So the only person in here that satisfies my hypothesis is actually Cindy, because Cindy is the one is drinking alcohol. He's drinking a beer. And if he's drinking a beer, then the conclusion would be that Cindy is 21 years old. So the conclusion that the police can obtain is Cindy is bigger or equal to 21 years old. Okay, so let's think about this in a more abstract way. What is an implication? Okay, and remember in the previous thing, we have this nice truth table, and then this is a good place for you to review it. And try to fill this truth table. Remember I said in the part 1 of the lecture, if P is false, Q is false, what is P implies Q? It's actually true. Okay. But now we're going to revisit if I'm going to negate something that involves implication, what do I do? And then the piece of information you need is to say, if I have implication, if P, then Q, if I take the negation of it, this is logically equivalent to P and not Q. All right? Okay, so now I'm going to negate this statement. As I have copied from left to right, if I bring negation in, for all become existence. And now I need to negate implication. And I'm going to use this particular rule here. So that's P and not Q. Okay, and that's it. Okay. Again, this is a solution typed in. So now let's go over a few definitions. Okay. So there's a car dealership, and then there's multiple statement. The car dealer says, if you did not buy your car from us, then you paid too much. The first thing to do is to translate the English into variables, okay? So my variable P is a statement, you did not buy your car from us. And Q is you pay too much. So the car dealer basically made a statement about implication, which is P implies Q. Okay. Oh, I don't have to write it because it's already here. Okay. And now let's translate back into the following relationship. If you bought from us, then you got a good deal, right? If you bought from us, that is not P, right? P is you did not buy from us, not P is if you bought from us. You got a good deal means that you did not pay too much, so not P implies not Q. That's the first one. Second statement, if you paid too much, then you did not buy from us. If you paid too much, this is Q. Then you did not buy from us, that is P. So this second statement is Q implies P. The third one, you did not buy from us, that is P. And you got a good deal, that is not Q. The last one, if you get a good deal, then you bought from us. If you get a good deal, that means it's not Q. Then you bought from us, that is not P. Okay. All of them looks a little bit familiar because those are different various concepts such as contrapositive, inverse, and so on and so forth. So it turns out, if I have statement P implies Q, then the statement not P implies not Q is its inverse. The statement Q implies P is converse. The negation is P and not Q, and the contrapositive is not Q implies not P. Again, those are important things that should show up on your cheat sheet if you are reviewing the material surrounding logic. Okay. Okay. Now, this is a quick review. We just saw this. So try to remember in 2 minutes, what is its inverse? If I have P implies Q, what's its inverse? What is converse? What is negation? And what is contrapositive? Okay. And now we're going to solve a question involving all this concept. The statement is, if a triangle has either 2 equal sides or 2 equal angles, then it is a isosceles triangle, right? Isosceles triangle is basically, by definition, mathematical definition, is it has 2 equal sides, which implies it has 2 equal angles. But let's translate the English statement into variables. The first statement, the first thing I'm going to do is P stand for a triangle has 2 equal sides. And Q, let me just give you this little bit statement. P is a triangle has two equal sides. Q is a triangle has two equal angles. And R is a statement. The triangle is an isosceles triangle. Okay, I'm just using a little bit abbreviation since I'm running out of space. Okay, the original statement is a triangle has either two equal sides or two equal angles. That means P or Q. And it's an implication implies R. So P or Q implies R. So now we need to generate what is a converse, okay? The converse, by definition, here is Q implies P. So in this case, it's R implies P or Q. And later on, we're going to translate it back to English. The inverse is negation of P or Q implies negation of R. That is inverse, okay? And then the contrapositive is not R implies not P or Q, okay? And now I need to translate it back to English, okay? If I translate back to English, first of all, let me copy my statement, inverse. Again, what I can do for inverse, I can also write out, bring the negation inside. So that became not P and not Q, which is the first part. And the last one, contrapositive, not R implies not P or Q, which is logically equivalent to, again, not P and not Q. Okay, how do I translate back to English? The first statement, R implies P or Q. So that means if a triangle is isosceles, then it has either two equal sides or two equal angles. Second one, if a triangle has neither two equal sides nor or two equal angles, then it is not an isosceles triangle. The last one, if a triangle is not an isosceles triangle, then it has neither two equal sides nor two equal angles. Again, the interesting part about this is you first translate the English statement into some logic expression propositions. You look at the corresponding converse, inverse, contrapositive in this abstract view, and then you translate back to English, okay? So the last one, which is actually very similar to the first question I have earlier, which is, if we go back to this question here, is how do we sort of derive sort of logic inference? And in here, what you want to do is input match the output, okay? Again, what is important is if one of the input is truthful, then whatever that person said has to be true. If that person is not truthful, then whatever that person says has to be false. We're going to use the same logic to solve the last problem. Okay, so first of all, you need to translate English into terms, in this case, implications. Okay, so there's three people on an island, and one says, if B is lying, so is C. Okay, so again, we're going to use three variables. I'm going to say this is P, means A is truthful. Q is, well, actually, in this case, they're overloading a little bit. Let's do the same thing. Let's say A is a variable. If it's true, that means A is truthful. B is a variable. If it's true, that means B is truthful. And a variable C is true when C is truthful. And A says, if B is lying, then so is C. So that means not B implies not C. Similarly for B, if C is lying, which is not C, then so is A. That means A is lying, that means not A. And C says, if A is lying, so is B. That is not A implies not B. So what you want to do, again, this is where you can pause the video and try to solve this on your own, is try to fill this truth table. okay? Let's do it a little bit. You know, if you again look at implications, if both if the terms in the implication is both false, the corresponding implication is actually true. So this is actually true. This is actually false, implies false, which is true. Similarly, you get this, okay? And you can do the next line, which is true, false, false, and so on. So after a while, it's going to take you a while for this question. After you filled all the truth table, what you get, true, false, actually I did this last one wrong. This is actually true. Okay, what you get is this entire truth table. And now we want to see if there is consistency or not. Okay, remember I said if A is truthful, then whatever A says has to be true. So let's start with the first one. A is truthful, whatever A says is true. Great, it's consistent, right? So input matches output. Now let's look at B. Whenever B is telling the truth or truthful, whatever B says has to be true. Again, it's a good match. Next one, if C is truthful, then whatever C says has to be true. Perfect match. So this is actually what leads to the conclusion. Is anyone telling the truth? All of them are telling the truth, okay? But what happened to the rest of the row? Okay, again, we're going to see some mismatch. Let's look at the second row. If A is telling the truth, then whatever A says has to be true. Great. If B is telling the truth, then whatever B says has to be true. But that's not true. There's a mismatch. So B is telling the truth, but what B actually says is false. That is a contradiction. So you can do the same thing for the rest of the rows to know that each of the rest of the rows has a contradiction. Then the only possible configuration is when everybody is telling the truth, which is the first row, okay? Another way to think about it, only the first row has all inputs match all the outputs. So we can conclude that A, B, and C are all telling the truth. Okay, so that's it for today's lecture. It's a little bit long, but because there's a lot of practice problems, and you know, try to pause the video and practice some of those questions. And I will see you next Tuesday. All right.